Polynomial equation with real coefficients with zeros at 5 and 3 plus 2i. Now if I have real zeros and 3 plus 2i as a root, that also means 3 minus 2i will have to be a root because those I guys have to have their conjugate pairs. That's by the complex conjugates theorem. So in factored form, I'd have something like x minus 5 times x minus the quantity 3 plus 2i times x minus the quantity 3 minus 2i. Once I distribute the negative, I get x minus 3 minus 2i, x minus 3 plus 2i. I know it doesn't sound much different than what I said last time, but on the previous one, the negative had to distribute through. So I'm going to start by multiplying this out, and we're going to multiply these two pieces first. So I like to use a box to multiply this so I don't forget any of the pieces. So just make a nice 3x3 box with the two pieces, two trinomials that we're multiplying. So x times x is x squared, x times negative 3 is negative 3x, x times negative 2i is negative 2ix. Then next row I have negative 3x, positive 9, positive 9i. One more row, 2ix, negative 6i, and negative 4i squared, because I times I is I squared. Now, I have 2ix and a negative 2ix. Those are going to cancel out. Similarly, the positive 6i and negative 6i also cancel out. That was part of the reason why the complex conjugates theorem works. You have to have those I guys canceling out. So I'm left with x squared minus 6x plus 9 minus 4i squared. But wait, there's still an I. But this time it's an I squared, and we know that I squared is negative 1. If I replace the I squared with a negative 1, it'll be plus 4, and I get x squared minus 6x plus 13. I'm not 100% done because I had 5 as another root, so I'm going to multiply again. I could make another box if I'd like. This one would just be 2x3 instead of 3x3. Or you can use a stacked method. So x times x squared is x cubed. X times negative 6x is negative 6x squared. X times 13 is 13x. Now I'm going to do the next row, negative 4x squared, but instead of continuing on the same line of work, I'm going to write it underneath, and I'm going to line it up with my like terms. So I'll have negative 5x squared, then positive 30x, and then a negative 65. So now I add x cubed minus 11x squared plus 43x minus 65. Okay. I'm going to try the same problem with a different strategy. So I still have x minus 5, but I'm going to kind of put that to the side for a moment. This strategy kind of works like completing the square, but it's backwards. So it's almost like disassembling the square. So I'm going to start by moving the 3 over to the other side. I get x minus 3 on the left and positive minus 2i on the right. Then I square both sides instead of square rooting both sides. Now on the left, I'm going to FOIL that. That's the biggest mistake people make on this method. They forget to FOIL. Don't be foiled by foiling. Plus or minus squared will still be positive, and then this will be 4i squared. Now 4i squared is negative 4. I get x squared minus 6x plus 13 equals 0. So there's the quadratic that has those 3 plus or minus 2i as the roots. Then I just have to multiply by another x minus 5. We just did that same piece. So how about let's use a box though this time. So we'll have x minus 5, x squared minus 6x and 13. So x cubed minus 6x squared, 13x, negative 5x squared, 30x, and negative 65. So we end up with x cubed minus 11x squared plus 43x minus 65. And that's the final answer. And you can kind of mix and match. So if you like this disassembling the square in the stacked method, you can use those together. You could do two boxes, a box for the second multiplication. Doesn't matter. But this is how we find a cubic polynomial with specific roots. Hope this helps.